My name is David Hamilton Nichols, and I am your MC for the afternoon sessions. We are very excited to kick off our quantum computing panel. Joining us on the panel are Rob Hayes, CEO and President of Atom Computing, Dr. Jonathan King, Chief Scientist at Atom Computing, and Yuval Bogar, Chief Marketing Officer at Classiq. Please help me welcome our panelists.
Hi, thanks for having us. I'm Rob Hayes, CEO of Atom Computing, and we're going to talk to you a little bit about the where we see quantum computing going, what it takes to build scalable, reliable quantum computers, how our customers and users of many different industries and verticals are eventually going to be able to use them and how they're going to program them to get value out of them, and then what are the kinds of things that they're going to program them to go do to create value. So I'll kind of kick it off, and then I think we'll leave some time for Q&A. So I'm going to talk to you a little bit about what are we doing and what is the industry doing to build scalable, reliable quantum computers. There's a number of different technologies that are out there today: superconductors, ion traps, photonics. Our company, Atom Computing, happens to be building something out of what's called neutral or cold atoms, where we're trapping atoms with optical tweezers. All of these different technologies and modalities are really aiming to do something similar, which is build general purpose gate-based quantum computing machines. And these are machines that can process very sort of large amounts of data or state information simultaneously in parallel to give performance that really just can't be matched with classical computing, to perform tasks that maybe can't even be done on classical computers in a practical amount of time. And the challenge that I think most of us have in doing this is, number one, is building very stable qubits. And qubits are sort of the fundamental building block of quantum computers, similar to like a transistor is in classical computing. And these qubits need to be able to hold the information for a long period of time. That's called coherence. And they need to have a low error rate. That's called fidelity. And they need to have error correction on them, which means when an error does occur, that as you're executing the code, you can detect that an error occurred and you can correct it. And this is something that's been built into classical computing and networking systems and memory and storage for many years. And this is technology that has to be also applied to quantum computing as we move forward. And so what many of us in the industry are doing is we're trying to build systems today that are in maybe the dozens or hundreds of qubits kind of scale and get those into thousands, tens of thousands, and eventually millions of qubits. And when you get to very large numbers of qubits like that, you can fit much larger algorithms and kind of code bases on it to have more and more useful computing capabilities. You also need a large amount of qubits in order to layer in error correction. You sort of need to over provision the system with physical qubits in order to get good, what they call logical qubits out of it. So there's a number of technologies that people are pursuing in order to go do this. And at Atom Computing, we're pursuing a wireless type of qubit. It's called a nuclear spin qubit, using atoms that are trapped in a vacuum chamber with lasers. And we can simply scale those up by creating more spots of light in the vacuum chamber. And these spots of light are individually controlled, so that you can write different gate information into the individual qubits and execute the circuits. Other technologies that people are pursuing use different kinds of technology, where in many cases they have cryogenic cooling and they need to cable up wires to all of the different qubits to control them. And those create different challenges for scaling in those modalities. So I'll kind of stop there and I'll pass it off to Yuval. And Yuval, could you talk a little bit about how people are going to program these systems moving forward?
Thank you very much, Rob. Thanks for inviting me and for passing on the baton. My name is Yuval. I'm Chief Marketing Officer of Classiq. We are a software company that helps build quantum algorithms. So hardware needs software to run. That's true in the classical sense, and that's also true in the quantum sense. And the power of the quantum computer, as Rob alluded to, is sort of proportional to, it's not the only measure, but it's proportional to the number of qubits. It's almost like a 50 qubit machine maybe is equivalent to a 10 mile per hour car. It's nice, but not super useful. But maybe a 1,000 qubit machine can go 50 miles per hour. Say, oh, I could actually use that and do something good with it. The problem is, how do you program these machines? Today, software is written by essentially telling the computer, connect this qubit to what's called a quantum gate, like an AND or NOT, or the quantum equivalent that does something on the qubit. Connect this to here, connect this to there. It's almost like a giant switchboard where you connect the wires. That's nice where you have 5, 10, 15 qubits, but it's impractical when you have 100 and certainly 1,000 or 10,000 qubits. You cannot continue to do it this way. So Classiq solves this problem, and that's why we're so excited to partner with companies like Atom Computing. When we look at how to solve this problem, we looked at the history. We all use Zoom or AirMeet in this case, and they run on CPUs that have billions of transistors. Well, how are these designed? They're not designed at the gate level. They're designed by having high-level functional models. Someone expressed what is it that they want to do, and then a software program synthesize that high-level functionality into the exact connectivity of the transistors or the gates. We do the same for quantum. We allow quantum engineers to express the what they want to do, and then we sort of compile it, we translate it into the how. And by that, we solve 3 problems. The first one is, how do you write sophisticated code for these large quantum computers? The second thing is, how do you make quantum software portable? Because we all hope that atom computing will be the winner, but we don't know that if that's going to be the case. And enterprises have to make sure that if they go on Atom, they maybe still want to be able to run on IBM machines, for instance. And the third thing, by allowing people to focus on the functionality and not the low-level coding, we make quantum more accessible to the sense that you don't have to be a quantum physicist, you don't have to have a PhD, no offense, Jonathan, to be able to do something useful in quantum. We want to make quantum accessible to chemical engineers, to logistics experts, to derivative pricing experts, so they can use their domain-specific knowledge to solve real problems on today's and certainly on tomorrow's computers. So I hope that's useful, and maybe I'll pass it on to Jonathan at this point.
Sure. I do actually have a degree in chemical engineering, so I'm not offended by what you just said. Yeah, so I think the next question we were going to address is, what do you do with a quantum computer, or what they're useful for? And I mean, obviously, quantum algorithm development is an area of rapidly expanding research right now, and in a lot of ways, the field is waiting for, and frankly starved for, the hardware to catch up to kind of validate and prove out a lot of these applications and use cases. But I think generally, some areas where we're pretty confident that there's going to be, a lot of impact. I'll just name maybe 3. One of them is like simulation of physical systems. Maybe the most obvious cases that there are some, systems like, let's say, simulation of the energy level structure of a molecule, which themselves are quantum mechanical systems. And so there's kind of a natural idea that a quantum mechanical system, such as qubits in a quantum computer, might be able to tackle that problem in a way that classical computers can't. Things like machine learning and optimization, I guess I'll list those as 2 separate things, are some of the use cases that I think have a lot of promise in the more near term. Without getting into the weeds too much, a lot of the power of a quantum computer comes from the fact that if you have a certain number of qubits, the vector space in which the computation happens is 2 to the nth power dimensional. And n doesn't have to be that very large before 2 to the n becomes a very, very large number. And since a lot of machine learning makes use of mapping problems into high dimensional vector spaces, there's a natural fit there. Optimization, some of the near-term algorithms, and when I say near-term, I mean things people are interested in exploring even in the era before error correction, kind of fall in the category of hybrid quantum classical, where you use the quantum computer to do something difficult like evaluate some cost function, and then using the output of that, feed it into a classical optimizer, which varies parameters, and then feeds back into the quantum computer. So yeah, I mean, there's so many industries in which these things can be useful. Obviously, optimization problems, heavily onto like logistics or financial portfolio optimization, chemistry, getting back to chemistry, kind of chemical industry, pharmaceuticals. It's very, very broad in scope.
Can you give maybe, Jonathan, maybe an example of what a chemical engineer might use a quantum computer for, and maybe a little bit more depth, but also for the layman audience that most of us are?
Yeah. Let me think of a good example. I mean, there's sort of the really, really like big examples, and maybe I'll talk about some of those. And there's kind of there's smaller scale examples that may be tried soon, and there's in the future with the error corrected larger scale systems. But the dream is that simulating the behavior of, let's say, catalysts or enzymes that for industrial relevant processes, like if you actually look through like where does most of the world's energy production go to, you actually find like relatively large fractions going to various chemical processes that like I don't know, things like nitrogen fixation or just developing a new catalyst. Let's say being able to understand in your computer the behavior of a new catalyst that lowers the energy cost for some process by like a few percent or something would be hugely impactful kind of on the world scale. So yeah, I would say catalyst design, pharmaceuticals, being able to kind of do computational studies to get some prediction in advance of actually doing lab work could greatly reduce the costs in those sort of processes.
And Yuval, what do you see as the biggest challenge when you engage customers or users that might want to get started on their journey to quantum? What are the biggest challenges that you hear from them as they're trying to figure out where to start?
So there are challenges on multiple levels. So first, because of the size of the strength of the quantum computers today, organizations can only solve what they sometimes call toy problems. So for instance, one financial services application for quantum computing is portfolio optimization. You've got 1,000 assets, and what's the optimal allocation there? Well, today, if you run this kind of algorithm in quantum computers, maybe you can optimize a basket of 10 assets. Well, that's nice to prove that the algorithm might work, but it's not useful yet. So they certainly need stronger hardware. Because they cannot solve real business problems today, sometimes they have challenges getting executive support. Oh, is this another AI where we're going to spend 10 years sort of figuring out what's going on before it becomes truly useful? And the third challenge is, which we help solve, is the manpower challenge. There are just not enough quantum physics PhDs in the world to all of a sudden meet that demand. And even though universities are stepping up and opening curriculums for quantum physicists, it's just not enough. So we want to make sure that a broader range of people can program useful algorithms with quantum. So these are some of the challenges that we see.
Thank you. And what about from a training kind of perspective? Do you see people feel like they're like, where do they go to get the skills they need to start programming these systems?
So first, there's a dramatic eagerness to get trained. We did a survey a couple of months ago of over 500 US professionals. And even those that says, yes, we're familiar, we know quantum, I think 90-something% said, if my employer has a training program for quantum, we're in. They want to learn more. It's hot. Some people see it as the next AI ML of, oh, I get in early, I can be super useful and really big expert tomorrow. Some of the IBM has a fantastic training program. They have a sort of a simple program that you can use for free. They have universities and courses, and I think they set a goal of training, 30 million people. So something fantastic on quantum. I dearly hope they succeed. there are plenty of resources, and it's an early stage industry. So I think there's a lot of openness. Even companies that you think would normally be competing are happy to collaborate and share information because they all understand it's about growing the pie at this moment.
Yeah, I personally took a lot of the IBM's Qiskit University courses online as I was coming into the quantum world, and I found it extremely beneficial for myself. I have a background in classical computer engineering. That's what my degree's in, and I worked at Intel for 21 years and led the Xeon processor roadmap for many of those years. And so I understand intimately well how classical computers work, and they did a nice job of like saying, if you know how this works, then sort of here's how you can bridge that knowledge over to the quantum world, not coming at it from a physicist point of view, but more of like an electrical and computer engineering point of view, which I personally found quite helpful. And then Jonathan and I actually had an opportunity to meet with one of the largest global IT consulting firms this morning and talk to them about their journey to quantum and how are they engaging customers to kind of onboard, their workloads and workflows into the quantum domain. And many of them had also taken some of the Qiskit University courses. And I think they had, Jonathan, say 400 or 500, what they call quantum enthusiasts, which are just volunteers within their company that are just really interested in quantum, and they're kind of classical IT software engineers today, but they're training themselves to be ready to help their customers on their quantum journey, which I think is fantastic. And I think all of us sort of in the community need to support that so that we can innovate at all levels of the stack kind of simultaneously and accelerate the future. So Jonathan, let me ask you this. You mentioned error correction. I think this audience is probably not all that technical from how it works, but could you kind of maybe explain why that's important?
Yeah, so it's sort of a fundamental fact that any quantum system has some limited amount of time after which its information is just kind of lost. Like they tend to be relatively okay. So our qubits tend to be do very, very well in this regard, but in general, like qubits eventually lose their information due to sort of just interactions with the environment. And so basically the state of the system will change unexpectedly. An error will occur. It could be analogous to those of you familiar with classical computing, a bit flip error. There's a little bit more subtlety to it than that, but it may be that any given bit can just go to the wrong state. And so kind of the era of quantum computing we're in right now, every system that exists, with dozens of qubits, up to like 100 qubits is subject to errors. And so anything we're doing right now with algorithms has to sort of fit within the capabilities of the system, and it has to be sufficiently robust to the error or to the noise that's in the system. Where we want to get to eventually is actually where classical computing already is to where when errors occur, they are corrected, and so that you can run circuits of logical gates. Like Yuval was saying, the end user may not in the end actually see those circuits, but you need to be able to run circuits of arbitrary depth and expect to get the correct result without an error. So there's a lot of theoretical work and a very few demonstrations of very small scale things that shows how you can periodically, first of all, encode a logical qubit into more than one physical qubit. In fact, it will probably be thousands of physical qubits. So there's some idea of redundancy. And then you need to periodically measure some things about the state of your system throughout the circuit to kind of extract a syndrome of errors and then do some sort of feedback to correct errors before they propagate. So, the longer term vision and a big motivation for why we are doing neutral atom qubits that are scalable is that you need to get to a system with many thousands of qubits, pushing beyond that towards 1 million qubits and beyond, where we understand we will have error-corrected logical qubits encoded into probably thousands of physical qubits each. And that's the place where we're really going to unlock the biggest longer-term applications. Actually, some of those famous applications that maybe people have heard of, factorization, Shor's algorithm, things like this, are really going to work once we reach this sort of error-corrected era.
Very good. So David, are we going to take questions from the audience in this session?
I think a few came in on the chat.
Yes, a few did come in on the chat, so we can. I think they've gotten some of those glitches sorted out. So let's just take those questions. And you want me to read them off to you?
Yeah, why don't you tee them up for us, and we'll jump in.
All right. First question from the audience is, what is the time horizon for commercial quantum computing?
Okay, well, I'll take the first stab at that. You know, traditionally, everyone says it's 10 years out, and I wouldn't have left my nice Fortune 500 executive job if I believed it was still 10 years out, and joined Atom Computing earlier this year. I think we're probably 2 to 3 years out from like early commercial value, early adopters, relatively small circuits that can run on the class of systems that'll be available in the next year or two. And it's probably more like 5 years out to have systems that are in the tens of thousands or hundreds of thousands of qubits to run much larger algorithms with a much broader set of use cases. So I'm gonna say 2 to 5 years is sort of the horizon that I see. Now, Yuval, you want to give your opinion on that one?
Sure. We're starting to see very early applications that demonstrate value. So for instance, Volkswagen just published a use case. Volkswagen, one of the things they do is they paint cars. So they have a paint shop, and they need to basically empty paint out of the paint machine and put new paint, right? They have to stop with the blue and start with the white. So they ran a quantum computing algorithm to help optimize the scheduling of the paint shop, and have achieved, they just published it very recently, about 20 to 30% efficiency improvement. They started from more of a intuitive scheduling done by a person to quantum computing, but you can start to see some of these come in right now. But as computers get stronger, as the software is written to allow them to use that strength, we'll see more and more coming into focus.
And if Dr. Jonathan, if you have anything to add, if not, we have other questions as well.
I think maybe we'll move on to the next one. Actually.
Okay. What is the right metric for measuring quantum computing performance? Not number of qubits?
So yeah, I guess I kind of wanted to take a stab on this one. I mean, there is no single metric. People want a number to compare and stack rank things. There is no single metric. I would say this: it's a combination of qubit number, gate fidelity, and also some of the other classical components that go in there that enable error correction, such as how well you can do measurement, how fast you can feed back, how fast that is relative to the coherence time of your qubits. So I think all of these things matter. It's kind of my opinion that qubit count is the big differentiating factor between different technologies. It seems like with lots of money in engineering, everybody can just keep pushing up their fidelities a little bit more each year. I think the sort of fundamental limitations that need to be overcome are more on the scalability side. And I guess to reiterate at an earlier point, that's what really drew me to neutral atom technology, is the scalability in that direction.
I would just add, I think it was IBM, I'm not 100% sure, came up with this quantum volume metric. So that's kind of one that's out there that's sort of a calculation or a measurement you can take on a system that gives you a performance benchmark that's intended to be apples to apples. So that's one. And then there's an industry consortia called QEDC, and they have recently created a benchmarking task force and released the initial benchmarks that people can run on quantum machines over time as they're available. And those will continue to evolve, but in the classical computing, that would be like the spec int rate or the spec FP or those kinds of things. And I think industry standard benchmarks that are independent of vendors are really important for being able to compare, different systems with common metrics.
Let's go on to another question, and that is, how can classical and quantum computing run in parallel together?
Sure. Maybe I'll take a stab at this one. Today, the option of using different CPUs or different processors for different tasks exists in everyday computing. I mean, when you run a game on your PC, You may have a CPU that's doing more of the general purpose work, and the GPU, the graphics processor, that's doing some of the graphics intensive tasks. All the useful quantum algorithms today are what's called hybrid algorithms. Some part of them run on classical, some part of it runs on quantum. Part of that is because classical CPUs are better at other things. We'll never run Zoom on a quantum computer. Classical computers are better at input-output, for instance. The other reason, and Jonathan alluded to that, is the coherence time. So it's almost like I would like to swim an entire Olympic-sized pool underwater, but guess what? I can't hold my breath so long. So I swim a few meters, I pop up for air, and then take a deep breath and do a few more meters. That's how algorithms work today. They run a little bit on the quantum. Whatever result gets measured, then it goes to a classical computer that does some calculations, feeds the quantum computer again, and so on. So that CPU, and quantum computer work in parallel today, and most useful algorithms today are indeed hybrid algorithms.
We have another question. Where are the components and auxiliary capabilities that will become as big as NVIDIA?
I don't exactly know what the question is, but I will tell you that I think NVIDIA is a great model for like a quantum computing hardware platform company like us, in that they kind of emerged in the same model that Yuval just described, which is a hybrid compute kind of model where you offload certain tasks that are highly parallel tasks and amenable to a GPU. To a coprocessor, if you will, and then you run other tasks that are more maybe serial in nature on the central processing unit in a classical computing sense. And I think the same thing is going to happen here, just like you've all described, is you're going to have like HPC clusters that are running some portion of a workload, and then there's going to be some algorithms or tasks that are offloaded to a quantum computer to develop results that couldn't be calculated on a classical computer. It would just take too long to be practical. And so when I think about like the future of our company, I very much look at the model that Jensen has done in building up NVIDIA as a fantastic co-processing company that's quite impressive with their developer ecosystem capabilities and the hardware that they provide. So I think it's a good analogy.
Yeah. And we are out of time on this panel, and just want to thank all of you, and also remind all of the viewers and attendees that you'll have some Eventbrite emails, that you have a link to provide feedback on the startups. So at Astor Perkins, would appreciate all of that feedback. So again, thank you to our panelists for a phenomenal job, and keep up the great work of what you're doing.
Thank you. It's a pleasure.
Thank you.